Hi, welcome to the EEVblog, an electronics engineering video blog of interest to anyone involved in electronics design. I'm your host, Dave Jones.
Hi, it's product review time, and this week we've got the smart tweezers from Advanced Devices. Let's check it out. So, what is the smart tweezers? Well, as you can see, it's a pair of tweezers with a meter attached to it. In this case, an LCR meter, a completely automatic LCR meter, and it has other features too. It does diode testing, continuity, and it even has a little oscilloscope display as well. So it's a pretty useful device, and as you can probably tell by the tweezers, it's designed for today's SMD surface mount components. You put the components between there and it'll automatically measure the component on the display. Pretty darn handy. It comes from a company called Advanced Devices in Canada, and this is their only product, and you probably haven't heard of them before, but this is a real nifty device and it's getting quite popular. I've had quite a few people ask me to do a review on this. Not only are they a Canadian company, check it out, made in Canada. Can you believe it? Made in Canada. I don't think I've ever had a piece of electronic gear made in Canada before. It's incredibly novel. Gets a huge thumbs up just for that. I love the Canadians. Now, of course, there are other LCR meters on the market, like multimeter style or little pocket ones with, test leads, and you try and probe your components like that. But that's really annoying. And so what they've come up with those devices is you can actually buy a similar sort of tweezer attachment for those. But they're still, they're messy. You've got cables all over your bench and stuff. And if you're like me, if you're assembling a board or something like that, and you've got hundreds of little surface mount components already on your bench there, ready to be mounted on your board, then, if you drag your test leads across your bench, bingo, you can wipe out all your components, and it's a pain in the ass, really. So these smart tweezers, completely self-contained, no test leads, just these little gold-plated tweezers, and they're very nice. Check them out. This is the straight version. They also, my one came with a curved version as well. I'm not sure if the standard one comes with curved, and they've also got what's called a precision type one as well, which I think has a more refined head on it, and it looks like really thick, solid gold plating. I've been using it for a couple of weeks, and there's no noticeable wear on it, but that's hardly a big test for it. But the probes are really, really nicely well designed. It's probably the best aspect of the product, and so it should be, because that's its primary use as a probable tweezer device. But hey, who cares about all that? Let's get to the fun part. So don't turn it on, let's take it apart. Okay, taking it apart's real easy. Just 3 screws on the top here, self-tapping screws, and bingo, there it is. Check it out. As you'd expect, a big LCD like that. Now, that's the first thing I really notice about this. There's no window, there's no protective window on there, so you're really reliant upon the glass surface of the LCD to actually protect it. So, it's probably, in that respect, it's not as rugged as it could be. Okay, so let's check it out. As you can see, you've got your 3 button cells here. Now, that's not the world's best battery holder. It's just got the 2 metal tabs coming straight out, just squeezing the batteries together, but it works. You can actually get a battery upgrade for it. You can get a rechargeable battery, an induction rechargeable battery. Now, as you can see, there's the piezo transducer in there, if you can see that. Yep, there it is. Little tiny piezo transducer, so it does beep and buzz and do all sorts of things. Now, as you can see, the LCD is just stuck down with some tape, with some just some double-sided sponge tape. That's pretty standard practice. Now, what they've got here is they've got a mechanism, looks like a mechanism holding the probes in place. So let's check that out. Now, if you try and get the rest of the board out, you don't undo this screw here, you undo another self-tapper on the bottom here. And the board should the whole mechanism should just lift out like that. And bingo, here it is. As you can see, they've got some sort of big custom mechanism here with there's the actual contact going across for the for one probe and the same thing on the other side for the other probes. That's really quite neat. They've come up with their own little sort of, custom enclosure for the custom mount for these probes, and it really is quite nice. Now, as you can see here with the circuitry, nothing unusual there at all. It's basically exactly what I expected. There's an MSP 430 processor here. There's just some basic analog stuff around here, and there's a slide switch over here which actually selects the voltage mode, and I'll talk about that later because that's one of the really annoying aspects of the product which I don't particularly like. And a standard jog shuttle down here which allows which you can push in like that to switch it on and off, and then you can rotate side to side to go through the menus, and then push again to select things. And that's a standard interface they use on all sorts of products, MP3 players and mobile phones, and I actually recognise that one. I've used it before in my own design, so it's all pretty standard stuff. There's not much in it. But the actual quality of construction is really, it's reasonably nice. I like it. They really haven't cut corners in too many places. Now, I'm not sure who actually makes the LCD, but as you can see, it's quite a high contrast one, and you can read it from, it probably doesn't show up on the camera, but you can read it from different angles, and it really is quite a very nice dot matrix display. I like it. Now, as you can see here, the spring contacts do actually have quite a bit of spring to them. They are bent in quite far, so they do apply a fair bit of force onto these batteries, which isn't too bad at all. Okay, now let's check out the operation of this device. Everything's controlled via this little jog shuttle here, which can move left and right like that, which calls up a menu system. Now, it allows you to scroll through the menus like this, and as you can see, it's got a whole bunch of menu options which we'll go into, but when you first turn the unit on, I was actually quite confused. It comes up with this advanced devices thing and it shows no measurement at all, and I thought, oh geez, it's taken a long time to boot, but no, it's just automatically, it'll automatically put up the reading once you actually probe something, which I guess is kind of neat, but I'd rather it have 0 on the display anyway. That's just a personal preference. So you push the jog shuttle in here and you come up with the menus. Now, as you can see, it's got auto set is like the big mode where it just automatically chooses whether it's capacitance, in this case capacitance, when I touch it with my fingers, and you short it out and it measures resistance. And that's probably the mode you most want to use it in because it works really well, the auto set mode. But let's have a look at some of the other modes, okay? Well, let's go into the menu, press it, and you go into measure, and you go into mode here, and you can choose all the different things. Auto mode, you can force it into different modes. Resistance, inductance, capacitance, diode, voltage, and the trace mode. So, if you want to put it into diode mode, there it is. It comes up with the diode symbol. It's got a diode symbol on the display, and what's really good about it is that if you short the probes together, like I am now, it tells you that it shorts out. Now, let's actually take a board here and let's probe a diode in circuit, okay? Now look, as you can see, it's come up with a diode symbol on the display, and the it's hard to keep the probes on. As you can see, the diode symbol on the display, it tells you which way around the diode goes. Let's put it around the other way, and there it is there. See, it goes in the other direction. So it tells you which pin corresponds. It shows you which whether the anode or cathode corresponds to which probe. It's really quite nice. But unfortunately, it's got a real big problem. It can't measure LEDs at all because it's got such a low voltage. There you go, it's switched off again. Such a low voltage threshold that if we try and measure an LED here in circuit, well, it makes, trust me, it makes no difference whether it's in circuit or not. It just can't measure, and that's a standard green LED at like 1.8 volts. It just can't measure it, let alone measure white LEDs and things like that. So I think that's a huge limitation, really, because when you've got a whole bunch of diodes on your, laid out on your bench here, ready to be soldered, you want to know which way around they go. And this is real handy for diodes, but not for LEDs. Now let's check out the system menu. Let's go in and go down to system here, and you can see that you can turn the sound off and on. You can actually swap the actual display left and right. So if you're left-handed, you can actually go left like that, and it's swapped it around. Isn't that neat? Now, other things in the system menu, you've got timeout. You can change the timeout from when it takes no reading at all to when it switches the thing off. In this case, it's 60 seconds. I believe that's the default setting. Service is like you can get the you can measure the battery voltage. You can actually adjust the offset, so you can actually trim the offset like that. The battery voltage you can measure 4.4 volts, which is rather neat. Now there's also a whole bunch of measurement options as well. As you can see, I'm just probing my fingers here, which measures the capacitance. It thinks it's primarily a capacitance, and it's giving us the series resistance as well, and then it's showing the measurement frequency is 10 kilohertz. Now you can change that measurement frequency and the secondary display as well. If you go into measure and you go into settings, you can change the test frequency. So let's say we want to change that to 1 kilohertz. Now unfortunately it doesn't have 100 kilohertz, which I think is a big limitation as well, but I'll talk about that later. Now see, it's changed the test frequency. Now let's go into, sometimes it doesn't respond to the button press, which I find rather curious. There seems to be like a timeout period there where it doesn't seem to respond properly. Maybe it's doing something in the background. Anyway, you can change the whether or not it measures the actual Q or the dissipation factor. So let's go into QD, and as you can see, the secondary display is now showing the dissipation factor of the capacitance. That's really quite neat. I like it. You've got, if you go down in the settings, you've got the test frequency, you've got the period, which allows you to change the measurement period, 2 seconds, a second, or half a second. That's it defaults to 1 second, I believe. So it's nice to be able to change the measurement period. I guess you get increased accuracy or increased stability with longer measurement period, but I haven't particularly tried that in depth. And it's got a hold mode as well. Now if you do hold, let's try that. Put it on 34 point, and it holds the display like that. That's really, it's really quite neat. And as you can see, 1.8. It's held it at 0.9. So it's, I guess there are quirks to that mode. It doesn't necessarily hold the last one. Yeah, it did that time. So I guess but generally that's a pretty handy mode. It's like a touch hold mode on an auto touch hold on a multimeter. Terrific. The other interesting feature of the display is that it actually has a bar graph as well, which is really quite neat. I guess you can see changes, but really the primary display is nice and big and clear. As you can see, it's just, it really is a beautiful display. A lot of effort's been put into how this, to the fonts and things like that of how this displays. I really like it. You can buy additional probes, as I've mentioned before, and they're really quite sharp. It's probably going to be hard to see on there, but trust me, they are really good quality probes, and they should last quite some time. Now the curved ones are quite good because when you use it like this, often if you're probing stuff on the bench, you want them to curve out like that, so that it's just nicer. The components don't flip around as much and stuff like that. So I guess that's a personal preference thing, but I really like the probes. Thumbs up. Okay, now let's check the accuracy of this. Now I'm actually using my microcurrent and measuring a component in circuit that I know is 10K 0.1%, and as you can see, it's basically spot on. Now if I change the range here on my microcurrent, it switches in a 10 ohm 0.1% resistor, and as you can see, it's pretty darn good. And I find that's pretty much over the range. It's much more accurate than its quoted specifications. It's really quite nice. I like it. Now, as for measuring components in circuit, it's just like any other in-circuit component tester. Sometimes it works, sometimes it doesn't, depending on what components are in parallel. Let's measure this tantalum here, which is supposed to be 47 microfarads, and well, it basically is with a series resistance of 7 ohms. So, and once again, it works in both, should work in both directions. There you go. So that is an example of one where it does actually work. Now, here's another example where I think it's probably going to work. That should be 100N cap in there, and you know, sure enough, it kind of is, you know, and it does work for some components in parallel, but not all of them. Here's an example of it measuring an inductor in circuit, and it's not too far off the mark in this case. So, you know, there are a lot of instances where it works, but I found a lot of instances where it just simply will not work because there's too many components in parallel. Now, let's try and measure the inductor in this small DC to DC converter circuit here and see what we get. It should be 10 microhenries, and it jumps around a bit, you see. It doesn't automatically lock in, so that shows that it's, you know, it can't measure everything. There was 8 microhenries there. There we go. No, see, it jumps around. It jumps around. It often gets very, very confused with some in-circuit components, so it doesn't always work. Now, that will change with the frequency as well. But you know, you can't rely on it as a 100% foolproof in-circuit tester. Let's turn it around the other way and measure it in the other direction. There you go, bingo, 9.1 microhenries. So, you know, you've just got to be careful when probing stuff in circuit. This thing is not infallible, and it's not unique to this. Any in-circuit component analyzer will be just the same. Now let's switch it back again, and hey, there you go, it's finally locked in. Maybe it had some residual charge in there somewhere, and it's fairly happy about it now. But yeah, just be careful. Now, an important thing to actually measure is the in-circuit test voltage, because this can have an effect. If it's too high, it can switch on PN junctions in the circuit when you actually measure stuff in circuit. Now, the unit claims to be around 320 millivolts RMS or 400 millivolts drive voltage. It's not entirely clear. Now, I've got it on 10 kilohertz test mode here. I've captured the signal, and it's about 266 millivolts RMS, or almost 800 millivolts peak to peak, which is larger. Well, it's, you know, it meets its spec, but I think it's larger than it probably should be. But the device seems to work reasonably well in circuit, so you know, I'm going to give it that. It does actually seem to work. Now, an interesting thing is when you this is just in auto test mode, so obviously it's going through some auto mode, and as you can see, it's switching between some high frequency and some low frequency thing there, as well as switching off in between. So it's doing some sort of compensation or some other, I don't know, measurement that it needs to do to get the display. And that's not just in auto mode either. I've just got it set to the straight capacitance mode, and it's doing the same thing. There's one other thing to consider with stuff like this, and it goes for SMD tweezers as well. Is the material a non-magnetic type? Because if it's magnetic, you can actually it can actually attract components and pick them up, and that can be really annoying. So I've got my little magnetizer, demagnetizer thing here, and I've tried to magnetize it, and I can't really. So I think it's like some sort of not easily magnetized material, which is great. There's one other thing it actually comes with, and that's a calibration certificate, which is really amazing for a device like this. It's got the serial number on it where it was tested, but it's not trace. I don't think it's traceably calibrated, so it may not be valid for a lot of companies who take that sort of thing seriously, but still, it's pretty good. But it doesn't give you the exact measurement readings. It just says better than 3%, better than 1%, better than 5%. So, it's not great, but hey, at least you get one. Now, one of the problems I have with this device is that it's it's not really capable of measuring low value inductors. Now, here's a 2.2 microhenry inductor, okay, and it measures that fine, but here's a 1 microhenry inductor. There we go, that's 1 microhenry. There you go. It's, it just doesn't know it's an inductor. It just can't measure that low, and I think that's a reasonably
problematic limitation. Now, I've got no problems with the low capacitance mode. As you can see, 1 picofarad is, a few picofarad is nothing for it. It can measure that easily. But inductors, its range probably isn't as big as I'd like. Okay, let's just do a quick comparison with an InCircuit ESR against the Bob Parker ESR meter I've got here. Now, as you can see, the Smart Tweezers is measuring at 10 kilohertz, and as you can see, it's 1.1 ohms ESR, basically. And the Bob Parker ESR meter, let's take a look very quickly. It's 1.1 ohms, so it matches fairly well. But of course, one of the big drawbacks with the Smart Tweezers is that its maximum frequency is only 10 kilohertz, whereas the ESR of capacitors is measured at an industry standard rate of 100 kilohertz. So really, it's just not capable of that. One weird thing it comes with is this little pocket clip like this. Now, you're supposed to I assume you're supposed to just hang the probe in there, and it's supposed to hang on your pocket like that. But it's just going to fall out. I don't know why they bothered. Now, actually, on paper, its specs aren't that terrific. We're talking 3%, 5%, like from 10 puff up to 100 microfarad is, less than 3%. I found it's actually better than that, but hey, they're the actual specs. Or 0.5 picofarads up to 5,000 microfarads is less than 5%. The specs aren't going to set the world on fire, but it seems to be much better than its specification, which is really quite good. The unit, of course, can also be used as a little mini oscilloscope in trace mode. So to do that, you actually go down to measure, and you go down to mode, and you go down to trace mode like that. Now, it'll actually say slide switch, because what you've got to do is you've got to slide this tiny little switch in there, and you can't do it. There's no way you can possibly get your fingernail or anything like that in there. So you've got to hunt around for like a little screwdriver, and then you've got to flick it across like that. And bingo, it goes into trace mode with a fixed plus minus 5 volt scale. I don't think you can change the scale, but you can change the time base by just pushing the jog shuttle. Let's see if we can speed it up. Yep, there you are. It's actually, it might not show up on camera too well, but it is actually flying through at a reasonably fast time base, and then you can slow it down, and that's rather neat. But I think that really lets it down. That slide switch is a terrible design aspect, the only really bad design aspect of this product, I think. I don't like it at all. Now, for those who are going to get excited about the oscilloscope capability of this thing, well, don't, because it's pretty much down in the gimmick category. Okay, here it is measuring a 10 hertz sine wave, and as you can see, it's hard to read, and yeah, it's displaying it, and yes, you can change the time base setting, but as soon as you do that, it just disappears. It's really, I wouldn't say hopeless, but it really is down in the toy category. Really going up in the high bandwidth stuff, 100 hertz. As you can see, it hasn't triggered properly, or it's ALS in. That's obviously ALS in. Okay. Just based on the sample rate. Now, I turn the sample rate up. Trust me, that's not a thing with the camera. I can't even see that display. It has disappeared. It is just, it's no good at all. That's a sine wave, but that, trust me, that is not the real deal. Okay? It's really no good at all. Except if you want to see very slow changing fluctuations down in the, couple of hertz, sub 10 hertz category. That's it. And I wouldn't get excited about the voltage ranges either. It's fixed on this plus minus 5 scale here. In fact, I think it's actually plus minus 7 or something like that. But as you can see, if we turn it down, it doesn't, it doesn't auto scale or anything like that. So you're really stuck with that one range. Now, in addition to the oscilloscope display I showed, which is a bit of a toy, it also measures voltage as well, and you've got to switch it to that mode too, and the manufacturer warns that you shouldn't, on regular LCR meter mode, don't put anything greater than, I think, 1.6 volts on the probes, otherwise you'll damage it. So, I think that's a pretty simple rule. Just don't use it for any voltage or oscilloscope type measurements. That's what your meter's for. Just, stick to the LCR meter functionality, I think. Now, Advanced Devices who make this, they're really trying to pitch it as sort of a semi-professional to professional level tool, because the support you get with it is quite good, and all the accessories you can get you know, different types of probe attachments, and you can get rechargeable solutions for it, auto induction docking stations and things like that for people who have high volume use. You're using it, you know, 100 times a day to measure, you know, components in production and stuff like that. And really, I think that's its main market. They should stick to that, because that's why you pay a high price for it, really. But you know, as a cheap hobbyist tool, well, it's, you know, it's clearly not marketed as a really cheap device. So let's sum up the smart tweezers. First of all, who's it for? Well, it's not really for your average hobbyist. I don't think. It's a pretty specialized bit of kit, because it's really designed for people who have a ton of components spread over your bench when you're assembling, or you're doing batch matching, or, you know, component matching or stuff like that. This comes in real handy, because you don't have to worry about probes dangling all over your bench. And the probe form factor is really very nice. It's very nice to use. So in that respect, it's unbeatable if you need the tweezer type functionality. I think it's fantastic. But as a general purpose LCR meter, I'd probably prefer one with the you know, a standard multimeter looking one with probes. I think they're you know, they're just a bit more versatile, I think. But and you can get probe attachments for those for standard LCR meter, multimeter. You can get tweezer attachments, sorry. So, you know, but it's pretty good. Now, the problem is, I think one of the major problems is the price. It's pretty high, so that rules out, you know, a lot of hobbyists and things like that. It's $320 street price. I don't think you can really get it under that. That's US dollars, so it's pretty high. You're paying a premium price for, you know, I mean, granted, it's a very, very good unit. But, you know, it might be pricing itself out of some markets, but for businesses and for world-heeled hobbyists and things like that, it's really good. And I'd recommend it. I thought it was a bit of a gimmick at first. You know, when I first saw it, I thought, oh, it's like those probe-type multimeters. You know, I just hate them. They're a gimmick. But this one's not. It actually works really well, apart from a few limitations which I've mentioned. And I find I'm actually reaching for it very often. It's a very useful bit of kit to have you know, to actually have on your bench if you can afford it. And it actually comes with a rather nice display, you know, a padded carry case, so you can sit that on the bench and it doesn't get damaged. So I think it's quite a useful tool overall. You know, it generally meets or exceeds its performance specification, and I give it a thumbs up. But price, oh. So, just how does the smart tweezers actually work? How does a typical LCR meter work? Now, I've covered this in another blog. I think it was blog number way back at 32 or something like that, but I'll go over it again. Now, the basic circuit, the basic functionality of an LCR meter, including the smart tweezers, is to have a function generator like this with different test frequencies and an output series resistor here, RS, and that goes into the device terminals, the device under test, the DUT. That's what they're the actual tweezer terminals, and it taps off the voltage from that, amplifies it, and feeds that into your analog to digital circuit, analog to digital converter, and your microcontroller. Now, it also feeds that signal into a standard feedback, a low power feedback current amplifier, and that actually gives you, and it allows you to measure the output or the current going through the device under test. Now, because the micro is generating this waveform, it knows what phase the test signal is, and so therefore it measures the voltage and the inductance, and also the phase, that's the key thing, of the voltage and inductance as well. And from those things, as I've explained in a previous blog, you can determine everything: capacitance, inductance, series resistance, parallel resistance, quantity factor, dissipation factor, a whole slew of things you can actually measure from just the voltage and the current. Okay, now that's terrific, right? You can measure all these things from just the voltage and the current. But how does the device know that whether it's inductive or whether it's capacitive. Well, I'm glad you asked that too. Let's take a look at it, how it works in auto mode. Okay, now this is a standard polar waveform, okay, based on the phase of the current through the thing. Now, if the current is leading, if it's positive in relation to the test signal, then it's going to be an inductive component. Now, if it's lagging the test signal, the current's lagging the test signal in any way, then it's going to be predominantly capacitive in nature. Now, of course, if the device under test is a pure resistance, okay, then it's going to have no phase angle difference at all. So the phase angle is 0, like this, and that represents a pure resistance. Now, if it's positive, okay, basically it depends on the quality factor. Now, if the quality factor is greater than 1 in this direction, like this, then the component is predominantly inductive with a small amount of series resistance. But if the quality factor is less than 1, but the phase angle is still positive, it's predominantly resistive with a little bit of inductance. So it knows what the primary component is, whether or not to display it as a primary on the primary display or the secondary display. Now, the same thing with the capacitance. If the quality factor is greater than 1, the component is predominantly capacitive with a small amount of, in this case, parallel resistance. Now, if it's less, the quality factor is less than 1, likewise, it's predominantly a resistive component with a small amount of parallel capacitance. And there's a series ESR in there as well, but that's essentially how it works. And for those playing along at home, here's a little bit more detail. When you actually measure, or when you calculate the phase, the voltage and current phases, and you measure them, what you come out with is an equivalent circuit of two series components, RS and XS. Now, if XS is greater than 0, it's an inductive component. If XS is less than 0, it's a capacitive component. But from those two figures, as I said, you can calculate everything, all sorts of things. This is only a small section of what you can actually calculate. Quality factor is the absolute value of XS on RS. Dissipation factor is 1 on quality factor. The impedance of the component, RS squared plus XS. Got that wrong. XS squared and square root. The series capacitance is 1 over 2 pi F. Absolute value of XS, the parallel inductance is XS on 2 pi F, and the parallel resistance, 1 plus, and so on and so on. You can calculate a whole bunch of stuff just based on fundamental voltage and current phases. It's a really neat technique. And this is how the smart tweezers works. Probably not as in-depth as this, but even the top end, the $10,000, $20,000 bench LCR meters, they're going to use this technique to calculate everything.